Now I begin to work through an example of a symmetric matrix of what we just talked about. Now, excuse me, I won't get all the way through the example, and I might not have time to insert the complete solution. But let's just work through the example and see what it involves. Okay, so we've got the matrix 4, 2, 2, 4. We find the eigenvectors. We take the determinant of this matrix. Well, let's determine the A minus lambda I matrix, and presumably we know why we do that. Because the premise is that A times whatever our vector is going to give us lambda times our vector, which is lambda I times our vector. So AV equals lambda I times V, so that A minus lambda I times V will equal a zero vector, which means that A has to be non-singular, which means that its determinant, which we write out like so, has to be equal to 0. Okay? Otherwise, the matrix would be invertible, and our eigenvector would be a 0 vector, and that's not an eigenvector. Okay? Eigenvectors have to be non-zero. In any case, you should understand that. It's not a difficult concept. It's not a difficult argument, and it helps you maintain your framework when you're working through this stuff. One way or the other, we take this matrix, we find its determinant, we simplify it, we set it equal to 0. In this case, the determinant, and this is called the characteristic equation, as I'm sure you know. This characteristic equation comes from this determinant factors into lambda minus 6 times lambda minus 2, so we get our two eigenvalues very easily. They just pop right out. Now, if we didn't get that, oh well, let's go over here. But we would have to, what? We get our characteristic equation, which is done in symbols now for a general symmetric matrix. We'll talk about that in a minute. And we have to go to the quadratic formula in order to find our eigenvalues. So if this had not factored, we would have been able to use the quadratic formula. Since this is a symmetric matrix, that has to work. We have to get real results. We're not going to get a negative discriminant, as we prove here. Okay? Now, having done that, we find our eigenvectors. We plug our eigenvalue back into this matrix, and we get a matrix that represents the fact that 4 minus lambda to 2, 4 minus lambda represents a system of equations. It says 4 minus lambda times V1 plus 2V2, where V1 and V2 are the components of your vector, equals 0. And 2 times 4 minus lambda, 2V1 plus 4 minus lambda V2 equals 0. So we have that matrix, and if we reduce that matrix, well, we get the eigenvector. So here is the system of equations I just mentioned. x1, x2 now instead of v1, v2, and that's perfectly good. Okay, what's the solution to this set of equations? For lambda equals 6, these are the equations. And look, the second equation is just equal to the negative of the first. If we reduce the matrix corresponding to this system, the second equation is going to reduce to 0, leaving us a free variable. Okay, and you should understand that, but one way or another you understand that the solution to this equation could be written x1 equals x2, because if x1 and x2 are equal, everything adds up to 0. And the same for this one, it has to be. So if x1 equals x2, what's our vector? Well, our vector is the x1, x2 vector. And x1 equals x2. Well, one possible vector is the vector 1, 1. Now that's a perfectly good eigenvector. If we know we're going to go to orthonormal vectors, if we're trying to find orthonormal vectors, which we will be doing, we could normalize this. The magnitude of this vector is the square root of 2. Just divide by the square root of 2, we get square root of 2 over 2, square root of 2 over 2, which is a normalized eigenvector. Right now we'll just stick with the eigenvector, 1, 1. If lambda equals 2, our equations become this, and x1 is going to have to be the negative of x2. So our eigenvector could be negative 1, 1, or 1, negative 1. If we want to normalize it, then it's going to be negative 1 over the square root of 2, or negative square root of 2 over 2, and square root of 2 over 2. Okay. So we get a set of orthogonal vectors. The dot product of this and this, it's negative 1 plus 1 is 0. It's orthogonal as advertised. And we can divide each vector by its magnitude to get an orthonormal set. We don't do that here, but we could. Okay. Now, what's our picture? Well, here's our picture. Here are our eigenvalues. 1, 1, negative 1, 1. Now I've got to figure out what in the world I'm doing here. Yeah, okay. So if we do this matrix times 1, 1, we get 6, 6. So 1, 1 transforms to 6, 6. And if we apply this matrix to negative 1, 1, we get negative 2, 2. You can multiply the matrix by each of these vectors and verify that this is what we get. Well, let's look at what this tells us. 6, 6 and 1, 1 have something in common. They have equal x and y components. So in fact, 6, 6 is 6 times 1, 1. And negative 2, 2 is 2 times negative 1, 1. Well, that's kind of interesting. How did that come about? What's that related to? Well, remember that lambda equals 6 gave us the eigenvector 1, 1. What's that mean? It means if you transform 1, 1, you're going to get 6 times 1, 1, and by darn we did. We didn't have to use a diagonal matrix or anything. This matrix did what it's advertised to do, because in a somewhat unusual set of events, I did the calculations right here. Okay. Then the matrix negative 1, 1, which came from eigenvalue 2, had better map onto 2 times itself, because that's exactly what it means for it to have eigenvalue 2. And right there we see that it just did that. Okay. Are the eigenvectors orthogonal? Well, I pointed to it here, but yeah, right there it is. Yes, they are. Okay, so symmetric matrix gave us orthogonal eigenvectors. We haven't orthonormalized them, but that's really easy. Just divide each vector by its magnitude. And it'll still be an eigenvector. It'll still, if you divide this by its magnitude, it'll still map onto 6 times itself. If you divide this by its magnitude, the new vector will multiply out to, will transform to 2 times that new vector. Okay. So again here, I just emphasize what it means for the matrix to be symmetric. The rows of the matrix that we started with become the columns of the transposed matrix. The rows of this matrix are equal to its columns. Okay. Again, any symmetric matrix has real eigenvectors, and I'll say, without defining what I mean by a full set, of eigenvectors which are orthogonal and therefore constitute a basis. Now let's make this an n by n matrix so we can be specific about what it forms a basis for. It forms a basis for Rn. And it can be normalized, so you get an orthonormal basis for Rn. And if you use the column of orthonormal eigenvectors, you can orthonormally diagonalize this thing using the same procedures we've already talked about a couple of times. Now we want to show that if a matrix is symmetric, and this is a general form of a symmetric 2 by 2 matrix at least, so for at least 2 by 2 matrices, we want to show, let's just say, that a matrix of this form gives us real eigenvalues. And it's pretty easy to do that. And then, generalizing it to higher dimensions, it's a little more complicated, but it's not particularly deep or difficult. Okay, so we'll do this in the next clip.